So from the 2000 AP exam, number 5, A, B, and C can all be done with just basic understanding of derivatives. So let's jump in. They say the curve is given by this function, xy squared minus x cubed y equal to 6. And in part A, show that the derivative equals this whole expression. So immediately when I look at the original curve, I'm realizing, okay, I'll need to use implicit differentiation because y is all jumbled in there with my x's. So if you're not comfortable with that concept, make sure you go back and look at our implicit differentiation videos. So I'm just going to start by copying down the problem. Now, we're going to take the derivative, so I can show that by using this symbol. I'm taking the derivative with respect to x, and I'll show that on both sides. This step simply says, okay, we're taking the derivative, we just haven't done it yet. Now let's actually take the derivative. So notice we're going to use the product rule for this first term. I have two different functions after all. So let's apply the product rule. So for this first term, we'll have to apply the product rule because we have two functions being multiplied. So always, we'll take the derivative of the first term, the derivative of x is 1, copy the second term down. Plus, now we'll copy down the first term, so x, and then take the derivative of the second term. Well, the derivative of y squared would be 2y, but since that letter does not match with the variable with which I'm differentiating with respect to, those letters are not the same, we have to follow it up with dy dx. So this is the chain rule, times the derivative of y with respect to x. Okay, so we took the derivative of the first term, let's do the derivative of the second. Pause the video and try it yourself. So notice that the derivative of y all by itself is just dy dx, or 1 dy dx. On the right side, the derivative of 6 is 0. Okay, now let's have a look. I have to get dy dx by itself, but right now I see it in multiple spots. So in order to get dy dx all alone, my first step I'll need to do is move anything that doesn't involve dy dx to the right side. So I'll move the y squared by subtracting it, and I'll move the minus 3x squared y by adding it. Once they cancel, we're left with 2xy dy dx minus x cubed dy dx equaling negative y squared plus 3x squared y. Now you might be wondering, well, why did we move them over? The reason for moving everything that doesn't have dy dx to the right side is that now I can just factor out dy dx on the left. I can just pull it out to the front from every term. We can't do that though if there's other terms hanging around on the same side of the equal sign. So let's factor now. I'm taking out dy dx to the front, and I'm left with 2xy minus x cubed. Everything else stays the same. Now it's factored, I can simply finish the problem and isolate dy dx through one simple division. These will disappear, leaving me with my final answer, dy dx equals negative y squared plus 3x squared y all over 2xy minus x cubed, which, comparing with the original problem, matches exactly, except they had just put 3x squared y in the front, ours is at the end, but notice the signs are the same. They're both positive, and then negative y squared is also there. So we'll put a check mark to indicate that we're done. So So what we did basically was keep our dy dx terms on the left. We moved everything that didn't involve dy dx to the right. Then we factored out the derivative, which we did in this step here, right? We factored it out and then simply isolated by dividing by whatever was left over after the factoring. Let's see how we did with the scores. So this part was worth 2 points. 1 point for the implicit, and then 1 point for getting it all the way, doing the factoring and the division. So that was a separate point for getting dy dx by itself. Okay, for the second part, for part B, find all points on the curve whose x-coordinate is 1. Then write an equation. So this is like a two-part question. First, we'll find all the points whose x-coordinate is 1, and then write an equation for the tangent line at each of those points. So first things first, let's find all the points whose x-coordinate is 1. Now notice, it didn't say find the slope or find the derivative. If it says find the points on the curve, we need to realize that they're just talking about the original function. Points on a curve is just x's and y's. So we're not looking here at all. Let's go ahead and find all the points where x equals 1. So that tells me I'm just plugging in 1 for x, and then we'll see what happens. So that's 1 times y squared minus 1 cubed is 1 times y equals 6. I want to find all the points, therefore I need the y value. So let's continue. It looks like we're going to have to factor. So I've moved my 6 to the left, and now let's finish. Y minus 3, y plus 2 equals 0. And so I find that y equals 3 and y equals negative 2. So to answer the question, the points on the curve whose x-coordinate is 1 are 1, 3 and 1, negative 2. It's just like any problem. If I want to know what the y value is, we just plug in x. For the second part, write an equation of the tangent line now at each of these points. So we're going to have two equations. One for the equation of the tangent line at 1, 3, and then a separate one for this point. Now it might seem a little confusing, but if you remember that the equation of the tangent line always follows the same formula, right? The equation for any line, we'll need two things for the equation of a line, which is a point that will go here and here, and then the slope. The good news is we already found our points, so I'm going to label them. This is like x1, y1. And now we just need the slope to plug in. So I have my points. To find my slope, I'll be dealing with the derivative. So at these different points, realize that the slopes can be different. Since the slope is given by the derivative, I'll plug in our first point and see what the slope is there. So copying down the derivative, which is 3. Now instead of x, I'm plugging in 1 squared times, instead of y, I'm plugging in 3. And I'll just go on plugging in those values carefully. 2 times x, which is 1, times y, which is 3, minus x, which is 1 cubed. So looks like my slope is 3 times 3 is 9, minus 9 is 0. And 0 over anything is 0. I don't even need to finish the problem. So that's the slope at the first point. At the second value, 1, negative 2, let's plug in and see what we get. So again, it's 3x squared y. X squared y minus y squared all over 2x y minus x squared. So 1 squared is just 1. 3 times 1 times negative 2, that's negative 6. Negative 2 squared is 4, so that's negative 6, take away 4 all over. This expression, that's 4, minus 1 cubed is 1, negative 4 minus 1, that's negative 5. So simplifying, we get a slope of positive 2. Now that's great. I have my slope, I have my point, so I have everything I need for a tangent line. Let's remember our formula. Once again, it's y minus y1 equals mx minus x1. But instead of m, we're really plugging in the derivative. Right? They're the same thing. The derivative is a slope. So let's find our first tangent line. I'm going to highlight what we're using. For our first tangent line, we're using this point, with this slope. Plugging it right in, I see I have y minus y1, so this is x, this is y, equals the slope x minus 1. So 0 will cancel everything out. Your first equation then is y equals 3. Looks like we have a straightforward horizontal line. For the second equation, we're going to use this point and this slope, or actually this slope. So plugging it right in, I see I have y minus y1 is negative 2. So that's y plus 2 equals 2 parentheses x minus the x value. And you are good to leave your answer like this. You don't have to distribute or anything. On the AP exam, FRQs get points for being equivalent to the final answer. So simplification is not necessary. Let's compare our work to the rubric now that we found our tangent lines. So it says here, when x is 1, those are the y values, so those are the points we came up with. That's right. At the first point, the derivative is 0. At the second point, the derivative was 2. So we get 1 point. Now I'm on the right side. We do get 1 point for showing this expression. You get another point then for solving for these two y values. And then you get 2 points for coming up with the tangent lines. So here the tangent line equation was y equals 3. And then the second one, it looks like it got cut off. But the second tangent line equation would be some equivalent expression to that. It could have been this, because it's just the same version, just I distributed and then moved the 2 to the other side. Either way, we would have gotten the points there as well. Great, so the last part of number 5 says, find the x-coordinate of each point on the curve where the tangent line is vertical. This being the key phrase. So let's talk about what it means for a tangent line to be vertical or horizontal even. So I've pulled up some notes that I want to go over with you, and it says, let's assume that we have a derivative that is expressed as a rational expression, right? So it's a fraction. So we know that tangent lines are horizontal where the slope equals 0. And so on this little drawing, you can see that can happen at a max, it can happen at a min, or it can happen at a point of inflection where it's neither a minimum or a maximum, but the tangent line is 0 nonetheless. So in the case where we're looking for a horizontal tangent line, we will always set the slope equal to 0. And if we're given a rational expression like this, if I want the whole thing to equal 0, all I need to do is set the numerator, the top, equal to 0. Because if I have a 0 on top, it doesn't matter what's on the bottom. The answer will be 0. Now in the case of a vertical tangent lines look like this. They can happen at continuous functions like that. Now, a vertical tangent line visually looks like this. The slope is undefined because it's something like, it could be 8 over 0, right? Where you're going up 8, but you're not moving. Your rise and your run are making you go up forever. Now, in the case of a vertical tangent line, it looks like this. So this should be familiar. It's where your slope is undefined. It can occur on a graph that looks like that, or it could even occur at an endpoint. For instance, for the curve y equals the square root of x, we have a positive tangent line everywhere else on the graph, but as we get closer and closer to the beginning, you approach this vertical tangent line. It also occurs on the cubed root of x, which is this guy right here. And then finally, it can occur at cusps, like y equals 2/3. And so on. So here I have a vertical tangent line. But when we have a fraction or a rational expression, we'll find our vertical tangent line by setting the denominator equal to 0. Why? Well, if the bottom equals 0, that answer is undefined. So keep in mind, if I need a horizontal tangent line, we set the top equal to 0. And if we need a vertical tangent line, we need the expression, the derivative, to be undefined, then we'll set the denominator equal to 0. So with that in mind, let's find where the tangent line is vertical. Now for my vertical tangent line, I need my slope to be undefined. So this will be undefined where the denominator equals 0. So I'll find the roots of the denominator for the slope to be undefined. We can find the roots by setting the denominator equal to 0. So from this step, there's a couple of things I can do. But what I need to keep in mind is noticing that I have more than one variable. I'll need more than one equation. So if we have 2 variables, then we need 2 equations to solve. We can use substitution or elimination, which are concepts that were first introduced way back in Algebra 1. But let's see what we could do. So one thing I could try doing is factoring out an x. But notice I'm no closer to solving for x or y. I haven't gotten anything really by itself. So let's try a different strategy. Since there's only one y, my best hope is to get y all by itself. And I'll do that by moving the x cubed and then dividing both sides. So I found that y equals x cubed over 2x. These x's will cancel, leaving me with x squared over 2. Now, as I said before, we need to solve for x and y, so we need one more equation. So let's call this equation 1. Let's go find equation 2. You should always look back to the original expression to find another equation. And indeed, here it is. So xy squared minus x cubed y equals 6. So now that I know that y equals x squared, I can plug that information into my original expression. So I'm using equation 1 and equation 2 to get something all in terms of x. So this is x instead of y. I have x squared over 2, but that needs to be squared, minus x cubed times x squared over 2 equaling 6. Okay, so one step at a time. X squared is x to the 4th. And 2 squared is 4, and that's times x. Minus, putting this over 1, multiplying straight across, I get x to the 5th over 2 equals 6. So I have really x to the 5th over 4 minus x to the 5th over 2 equaling 6. Now I want to clear my fractions, so I'll multiply every term by 4 so I have no more denominators left over. This will leave me with a 2 in front, and that becomes 24. Ooh, we can combine like terms. X to the 5th minus 2x to the 5th will be negative 1x to the 5th. And in 2 steps, I'll be done. First, I need to get rid of the negative. So that's going to be x to the 5th equals negative 24. And in my last step, I'll take the 5th root of both sides for a final answer of x equals. Now I don't need plus or minus because that's for even roots. So use plus and minus when taking even roots on both sides. But since this is the 5th root, our final answer is simply the 5th root of negative 24, which is a real number. We can take odd roots of negatives. So let's see if we answer the question. Find the x-coordinate of the points where the tangent line is vertical. We ensured we had a vertical tangent line by setting the denominator equal to 0 so that the slope was undefined. And when we did that, we found an equation with 2 variables. So we used a second equation and substitution to find our x value and answer the question. Let's see how we did based on our rubric. So we got the answer. Awesome. You can pause the video here and kind of look more briefly on the left side, but I'm going to go straight to the points on the right. So we got 1 point for setting the denominator of the derivative to 0 because we wanted our slope to be for our vertical tangent line. We then got a point for solving for y and then substituting it in. Notice you could have also solved for x, although that was a little more complicated. And then we got a final answer for getting our x-coordinate of 5th root of negative 24. So in this case, we got all 3 points. I hope that was helpful.